We are live on YouTube now.
Hello, good morning.
Yes, sir. Good morning, sir.
Okay,
Uh,
Mr. Chetan.
yes, sir. Yes. Sir, we'll start the session in 1 or 2 minutes. Participants are still joining, so
Okay,
let's wait a few minutes.
your voice is echoing.
Is it okay, sir, now?
No, it is same. In fact, I hear my own voice. Also.
Sir,
Hello. Yes.
yes, sir. Yeah, I'll start with a short introduction and then you can continue, sir.
Okay, no problem.
Thank you all for being here for this session. We would like to warmly welcome our speaker, Dr. Radha Krishna from Space Astronomy Group at the UR Rao Satellite Center, ISRO. Dr. Radhakrishna is a distinguished expert in the field of X-ray instrumentation. His work focuses on the development and optimization of cutting-edge X-ray instruments for space missions. Dr. Radhakrishna's contribution have been pivotal in enhancing the capabilities of space-based X-ray observation, enabling more precise and detailed observation of celestial X-ray sources. He will be discussing X-ray instruments, providing us with valuable insights into the technologies and the innovations that drive the advancement in the X-ray astronomy. Thank you, sir, for being here.
Yeah. Thank you very much. Uh, I have some problem. I hear my own voice here. So, is there any mobile or something which is on there?
Sir, are you joined with two accounts maybe?
Uh,
Uh,
Whether myself?
yes, sir, because
Oh,
we did not hear any other echo from our side.
oh, one sec. Just one sec. Oh, I think yes. Hello.
Yes, sir.
Now I think it is clear. Yeah. Sorry. In fact, two Zoom accounts I had
Yes, sir. Yes.
logged in. Yeah. So I'll share the slides.
Yes, sir.
You can see the slides now.
Yes, yes.
Yeah. Good morning, everyone, and thank you for the introduction and also, this opportunity to speak to you all. Just for my understanding, I believe you're all uh, in your MSc or PhD, probably. So, if I may know.
Sir, we have
Hello.
UG and PG level student mostly.
Okay, okay, okay. You have X-ray astronomy as part of your coursework, or it is a topic which you're all interested.
Sir, some of us, yes, we did a Google form and majority of the student responded that they do have some experience with it.
Okay, okay, fine. What I am trying to do is, you already had some background talks or introductory talks about X-ray astronomy yesterday. So today, my I will cover on some of the instrumentation aspects in X-ray astronomy because they are very different from the instruments which are used in other areas of astronomy. So we have some expertise here. So I will share some of the first level information. It's not like in-depth aspects of the instrumentation. Some of the key elements, the techniques and key elements of X-ray instruments. That's what I would cover. So you all know, it's just to for completion's sake, we'll start with this introduction story of Galileo. Probably, that is the beginning of the modern astronomy using instruments. He uses telescopes and looks at the sky, and he sees moon. He looks at the moon. He looks at Jupiter. He looks at the planets around Jupiter, and from there the interest has started to understand how these planets go around, and hence came Tycho Brahe, a detailed observation, and Kepler comes up with the planetary laws of planetary motion, and Newton explains how they remain in the orbit. So all these things, all these developments, so the whole thing started from the observation through instruments, that is from Galileo. And if you know the modern astronomy, the modern astronomy and astrophysics relies heavily on cutting edge technology and the instruments and the instruments. And you have a lot of ground based telescopes. uh, See, unfortunately, this online meeting, the interaction will be limited during the presentation. Anyway, we can keep the discussion towards the end or in between. How exactly you want? Hello,
Sir, we'll
hello.
keep the
Sir,
question to the end.
we'll
Toward the end. Okay,
keep the discussion at the end.
okay, fine, fine. Right. So, so ground-based astronomy, we have large telescopes established around the world in different places. The locations which are far away from cities and pollution and light pollution, air pollution, etc., and also mountainous region where you have less atmosphere at the higher altitude. And while we have so many ground-based observatories, big telescopes, you can build very big telescopes, you can maintain, you can upgrade them. Still, we have to go to space. Why? We have simple reasons. One is you can't avoid atmosphere on the ground, so you will always have atmospheric effect, which will, the atmospheric turbulence, all these things will cause, the disturbance. And also the atmosphere absorbs certain wavelength, certain, especially in near IR, etc. And um, uh, also, you have multi-wavelength. The each of the if you look at the electromagnetic spectrum, you have the spectrum, based on wavelength, it varies from radio wave to gamma rays. And the sources also, the celestial objects, they all they can emit in any of these wavelength, or many of these wavelength. And you have optical emission and you have X-ray emission. If you look at the typical black body spectrum, the higher the temperature you have, higher the peak emission. So which we all know that. And so you have X-ray emission expected in sources which contain an extremely hot gas at temperature from a million to hundreds of million Kelvin, what is called thermal bremsstrahlung. And also X-ray emission can happen if there is a synchrotron process, that's a very intense high magnetic field present in the source. And of course, gamma ray emission and radio emission are the other waveband emissions which are of interest. So while we have emission in all the wavelength, the atmosphere, the ground-based observatory cannot, see all these emissions because of the of course, what we discussed, the absorption of X-rays and gamma rays, and also the extreme ultraviolet rays in atmosphere. And then you have visible which are reaching ground, but however, because of atmospheric turbulence, you will have the what is called twinkling effect. The atmospheric effect will affect. And then in near IR, you have a lot of absorption because of the atmospheric constituents. So if you want to avoid all those, you have to go to space. And of course, and also the far IR also, you have to go to space, so that you are able to avoid the atmosphere and effect of atmosphere, and observe the objects in different wavelengths. And when we observe all these different classes of sources. Solar system has its own interest to study the origin and evolution of our own solar system. And a lot of planetary studies, planetary missions will be there, planetary studies to understand the origin of the creation of the planets and evolution of the planets. Then other stars, the galaxies, nebula, and the certain the exotic features like globular clusters, and the compact objects like white dwarfs, neutron stars, black holes, and the most intense objects like active galactic nuclei and the binary star systems. These are different systems, star objects and systems which are of interest to study. And then coming to the physics of it, the high energy now we are looking at the X-rays in this talk. So basically, the high energy astrophysics, it studies the universe in extreme like extreme temperatures, pressures, etc. And our understanding of the behavior of matter at extreme densities and temperatures, high velocities, high magnetic fields, strong gravity. So these are all are of our interest to study the objects in this extreme environment, and the objects which we already discussed, the objects of interest, and what what are the processes which are of interest. We have nuclear fusion and thermal emission, that is the thermal bremsstrahlung, and then we have gravitational collapse, supernova explosion, and black hole dynamics, accretion disk dynamics. And I understand some of these things you would have already got introduced to in your classes or the earlier talks. And then the particle acceleration and the magnetic field, these are some of the processes which we have interest in studying. And also the energy of electromagnetic emission from these processes. In higher energy, we classify it in soft X-rays, that's 0.12 to 10 keV, something like that, and hard X-ray 10 to 50 keV, and 50 or even 100 keV, and then gamma rays, typical gamma rays emission are 50 keV or higher, and very high gamma rays more than 50 keV. So these are all the emission sources, processes, and energy range. And coming to the techniques, so in astronomy, we have four different techniques. We have timing experiment, we have spectroscopy, we have polarimetry, and we have imaging techniques. So what are each of these techniques? Briefly we'll look at it. So the timing is nothing but the flux variation with the time to study the source variability. So we have X-ray flares, X-ray burst, X-ray gamma ray burst, and pulse timing of neutron stars, and orbital period of binary stars. These are some of the things which can we can study by studying the variation of the flux with the time. If you see in this plot, as you observe the same source, and you suddenly see a variation. So by continuously studying an object for longer time, you can study the kind of things like orbital period or pulse timing of neutron stars, etc. So for example, here, this corresponds to this region. As you see, this is the region which is being observed, and this is the flux you are seeing. But suddenly you are seeing a brightened object here. So you have increased intensity. So this is why we go into these studies, the timing studies. And then the spectroscopy, again, you are familiar what a spectra can tell. So spectra can tell, of course, the elements present in the stars or in the medium. And for example, here, if you see here, this is an observation by Chandra telescope of Cassier. And here, if you see, this is the spectrum. And if you look at the image and the spectrum together, you can see which region has rich in what element. So these are important in understanding the star formation or stars. And then of course the spectroscopy, with spectroscopy one can also study other things like the redshift, and also in recently in exoplanet studies, you can study the exoplanets using spectrum. That is, by spectral shift one can study what is called radial velocity method to detect the exoplanets. And then the imaging techniques, the images tell many stories. So imaging is basically the nothing but the photography of the region of the sky, or the an extended objects which can show you different features which will be of interest for further study by spectroscopy or other techniques. And this is the photograph of picture of sunspot here. And as you can see, to understand these features, if you look at the polarimetry study, when you do polarimetry study, you can know that these features are nothing but the magnetic field and its orientation, which causes these. So you have polarimetry study also, where you look at the polar state of the light uh, in different wavebands again. So these four techniques, and with these four, taking these four techniques, there are lot of missions which many of them may be familiar to you. In X-rays, there are a lot of major missions happened. If you see Chandra X-ray Observatory and XMM Newton, two observatory class, which is working even today. It is looking at the sky for long term, look at various sources, and then we have many other X-ray mission, RXT, Integral, Swift, GLAST. So like that, many missions. So this is not limited by the list I have mentioned here. And then we have Astrosat, our own Astrosat, which had X-ray instruments like SXT, LAX-PC, CZTI, SXT soft X-ray telescope, large area X-ray proportional xenon proportional counter, and cadmium zinc telluride high imager. It's a high energy, and scanning sky monitor is another soft X-ray or low energy X-ray monitor. And then we have recent big missions like IXP, that's a polarimetry mission, and Exposat, once again India's Exposat polarimetry mission in medium energy. And then we have solar missions also in X-rays, and some of the examples are SOHO, Hinode, and SDO, and Aditya L1. Aditya L1 is our mission. We have X-ray instruments in these missions. So, as I mentioned, it is not limited to these missions alone. There are many more missions. And currently, there are many high energy instruments, X-ray instruments in the orbit. Currently, they are all working. So if you look at the Astrosat, you have LAX PC and SSM. Both are, you call them timing instruments. They look at the flux variation with time. LAX PC has one of the highest effective area, which can give huge sensitivity advantage. And then imaging instruments in Astrosat, that is SXT and CZTI. You can see the energy range also here, what it covers. And then there are a lot of spectroscopy instrument which have been developed and flown in various missions. We have SXT, which is both spectroscopy and imaging, of course, on Astrosat. And then expect X-ray spectroscopy and timing on Exposat 0.15 kV. And then class is even though it is flown on Chandrayaan 2 orbiter, it is working even today. And because that is once again X-ray instruments within this energy range. It's a large area spectrometer, and the same similar configuration, same concept has been adopted in Expect payload on Exposat. Then XSM is on Chandrayaan 2. It's a small X-ray spectrometer. Similarly, on Aditya L1, we have low energy X-ray spectrometer based on these are all different detectors. I'll come to that little later. And then we have high energy X-ray detectors on Aditya L1. And then we have Polix, that is on Exposat, which is a polarimetry instrument, medium energy 8 to 30 keV. These are all presently in the orbit in these spacecrafts. And there are some predecessors, just to have some knowledge of what has been done before these major instruments on specific scientific missions. We had IXAE, Indian X-ray Astronomy Experiment, based on proportional counters on IRS-P3 in 90s. And then we have GRB monitors on SROS satellites again in 90s. So these are all the instruments what has been flown by within from India. And again, coming back to the techniques, what we looked at, the timing. In timing measurement, important thing is time resolution. Time resolution means what short time you can detect the flux variability, how short that time duration is, the capability of instrument which can give events within a particular time. And the spectroscopy is, the requirement is good spectral resolution, that is to resolve to closely spaced energies. We are talking about X-rays here, so we'll talk in terms of energies. And then imaging angular resolution in the sky. And the polarimetry, we look at the minimum detectable polarization. Minimum detectable polarization, if a source has 1% polarization, particular source of a particular strength has 1% polarization, whether that can be detected. So that is decided by the instrument's minimum detectable polarization capability. So for all these four techniques, that is timing, spectroscopy, imaging, polarimetry, what is required is large effective area, uh, that will give enhanced sensitivity. We'll maybe little later we'll really discuss what exactly you mean by effective area, because you have a geometric area, that is say, let us say your detector size is 10 centimeters square, that is geometric area. But effective area has to take into account many other factors also, like efficiency, etc. Then you look for energy range, the energy dynamic range, what energy to what energy. So these are common things what we need for all these different techniques. And also other performance parameter for any of these instrument is, the we just talked about effective area, that is basically the sensitivity. The sensitivity you can define as the minimum detectable signal for a given source against the background. So as you have many effect on the source while doing during source observation. We have many uncertainties. That is, one is Poisson noise, that is from the source itself, and then the instrument noise, you have background noise, you have. So you should have sufficient sensitivity where the source flux is, source, the photon values. Let us say you have certain sigma sensitivity, 1 sigma sensitivity, 2 sigma sensitivity, 3 sigma sensitivity. If you say 3 sigma sensitivity, then 99.7%, that's a typical 3 sigma value, is of from the source is above the background. So you have higher certainty that the source detected is indeed, the flux detected or photon detected is indeed from the source of observation. So these are some performance parameters which we look at when we talk about the X-ray instrument. And yeah, once again, coming back to the effective area, the effective area is basically the depends on the collecting area. That's the total collecting area of the, if you have optics and detector together. And then the efficiency also, say, let us say you may have 10 centimeter square geometric area, collecting area, but the efficiency of one instrument is poor compared to another instrument of same 10 centimeter square area. So if you count the efficiency also, then then what you get is effective area. So effective area is nothing but geometric area multiplied by the efficiency. When you say efficiency, efficiency of the optics, efficiency of the detector, all these things come into picture. So all those factors you have to factor into, then you get effective area. This is just a sample, the effective area comparison. The advantage of having effective area as a parameter is you can compare different instruments across different energies. Here, if you see, you can see XMM, XMM and Chandra. You can compare them. because both of them are similar instruments. Both of them have X-ray optics. Both of them have X-ray detectors. But how do you compare which is good where? So that's where you take effective area into consideration. So when you plot them, you have a true picture of what is the strength of each instrument, and you have a good comparison for different instruments. So that is about the some of the key aspects of the instrument, the sensitivity, how especially the sensitivity aspect. And then coming to some of the subsystem, I'm not sure how, what to what depth I have to go, but I will try to keep it in a very the first level information as such. So any standard instrument, any instrument has three major elements. You have optics, you may have optics, you have detectors, different types of detectors, and then of course you have electronics to process the signal from the detectors. And this is a picture of Chandra telescope. Chandra has X-ray optics here. This is where the optics is, and this is where the detectors are located. And then you have electronics located. Some of them are here. So and then probably I'm not sure where exactly the rest of the electronics. Yeah, here only we have the lot of electronics located. And any instrument, when you develop these instruments, some of the technologies what you look at is, apart from major optics, the sensitive detectors, and many of these detectors have to be operated in a certain temperature, then only it will give the performance. That means you need to have cooling, and then also you need to have your system which has to sustain the space environment, like radiation hardening. You have a lot of the ionizing radiation environment, like high energy protons, electrons, etc. So your instrument should sustain these radiation. And then you have to have data processing and analysis tool. And then very importantly, you must have calibration of calibration sources. These are other things which you have to use. And then you are looking at a source which are very far away, and which are which has to be observed through precision pointing, because if you there are a lot of sources nearby, you don't want to look at them. You don't want your data to be corrupted by them. So you should have precision pointing for the source which you want to look at. So these are the common technologies which are required. But each of these, you look at better and better every time. When you talk about optics that has been flown, when you go for future instruments, you look for larger optics and much better finish, much better, which can give much better resolution, angular resolution. So you keep looking for improvement in each of these technologies, so that you can do better and better than what has been done. And optics, in when it comes to X-ray, X-ray optics are not typical lens and mirrors. So X-rays can be reflected with the grazing incidence only. So here, if you see here in this bottom left picture, when X-rays hit in a grazing angle, that is a degree plus or around that, then it can be slightly deflected. So since it is grazing incidence, uh, okay, I think there's a duplication. And since grazing incidents, there are different configuration people have worked out. And Volter 1 is a configuration which is most optimized configuration, which has a parabolic segment and hyperbolic segment here, if you see here. So the X-ray parallel beam X-ray coming and hitting the first segment at grazing incidence is deflected, and then the second segment is further deflected and gets focused. So this is called Volter configuration. So you have to have a arrangement. If you see, typical normal optics, for visible IR, etc., you may have a single mirror in parabolic shape, and all the parallel beam coming will get deflected into the reflected into a focal point. So that can happen. Or you may have a lens system which will which will refract light and gets focused. But in X-ray it's not possible. So you must have a very complicated system. That means multiple shells. Say if you have only one set of shells, you have very limited area providing, because this is just grazing incidence of 1 degree, let us say. You are providing very limited area, so you must have many shells like this. And if you go back here, you can see many shells are provided, so that you are increasing the area. As we have seen before, the sensitivity depends on the effective area. The effective area depends on geometric area also, apart from efficiency, geometric area also. So larger geometric area, if you want in X-rays with the optics, you must have these many shells arranged. And these are pictures of shells in XMM Newton. This is in S60 on Astrosat. And then there are other things, other techniques also used, but they are not perfect imaging system as such, but they are used to restrict the field of view in the sky. For example, here collimators, mechanical collimators, which are nothing but open apertures. So these can be restricted by designing these collimators appropriately. You can restrict the field of view on the sky, 2 degree by 2 degree, 3 degree by 3 degree, like that. So this is one such system used. And then there are coded masks. Masks are used for imaging. So you have a coded mask. It is coded such that the shadow of the sky is unique. That is, the source here has a unique shadow, and source here has unique shadow. So by analyzing, you get back the original image of the sky or the object. But these cannot provide the kind of resolution what is typically obtained by these kind of optics. So that's about X-ray optics. And then coming to detectors, briefly look at this is a little more technical in nature, but nevertheless, I think it is good to have an idea what are the things which are used in these X-ray instruments. And you have typically what is called ionization-based detectors. As you know, any any object, when X-ray passes through an object, it ionizes. And we are exploiting these in a certain detectors, like gas ionization detectors, and then the solid state detectors like semiconductor detectors, where X-ray interacts and produces a detectable signal. And then there are scintillation detectors, where the scintillation light is produced when the radiation interacts, and the subsequent interaction happening within the scintillators. And just a little more on that, and all the ionization detectors utilize the same principle. So the on the right side it shows the schematic, and you have X-ray photon hitting the medium of the detector. Medium can be gas, or it can be a semiconductor. And as you know, the X-ray photon interacts with an atom. So this is the way it can interact: photoelectric effect, Compton scattering, and pair production. And this depends on the Z value of the detector atoms, and also the energy of the X-rays. So typical lower energies, that is 10, 20 kV, etc. You have photoelectric effect dominating, and above that Compton scattering dominating, and very high energies you have pair production. So what happens is, once this interaction happens, you have free charge carriers produced. That is, when photoelectric effect happens, you have a photoelectron emitted. Then that photoelectron further ionizes. So ionizes means you have ions and electrons. And in gases, they are electrons and ions. And in solids, that is in semiconductors, we call them as electrons and holes, absence of electrons. are produced. And these charge carriers are collected by applying electric field. So you have to collect these charge carriers, you have to separate them and collect it, and it produces a charge or current pulse in the external circuit. So that is analyzed. That output pulse is, once you have output pulse generated, then you have all the electronic system to take care of further analysis. And again, gas, little more on gas ionization detectors. Here the gas is the medium within this, and you have a simplest form, a single wire, anode wire, and this is the cathode, all around cathode. This anode is given high voltage. So when an interaction happens, you have electron ions pairs produced. Ions will move towards the cathode, electrons will move towards the anode. As it nears the anode, we have very high field very close to anode. This high field gives sufficient energy for the drifting electrons, and you will have what is called avalanche multiplication. So you will have more electrons and ions produced. So you have a single photon producing few number of ion and electron, and those electrons are multiplied, so you will have a very good detectable signal. So these are typically operated in multiplication region, and so they are called proportional counters. So these proportional counters are uh, they are used in SSM on astrosat, lax PC on astrosat, and polix also. We are using this same principle to detect a single photon. And then we when we talk about semiconductor detectors, we have the what is called um, uh, um, depletion region. So you have electron and holes. When sorry, I mean we come to uh, in semiconductor we have p-n junctions, semiconductor like silicons, and there are other semiconductor detectors like CDT and CZT, CDT, cadmium telluride, CZT, cadmium zinc telluride. And with silicon itself, there are varieties of detectors like silicon pin, silicon drift detectors, CCD. CCD is silicon-based detectors. CMOS is silicon-based detectors. CMOS, what you see in most of your mobile cameras and all, they're all CMOS sensors. Earlier digital cameras had CCDs. And here the main principle is, you create a depletion region. Depletion means when when we have p junction and n junction, a little into your solid state physics, when you look at, you have p junction and p and n material come together and they form pn junction. In pn junction, at the junction you have charge, the electrons and holes going across each other, and they recombine, and they are free of charge. So when you apply reverse bias, you have this depletion region. Depletion, it is called, there are no free charge carriers. So you are depleting that region of free charge carriers. And once you have depletion region, let us say this is a simplified diagram. You have a structure here, pin. This is PIN structure here. So you have depleted region here. Entire region is depleted. And when an X-ray photon hits, you have charge carriers produced. Since these charge carriers are because of X-rays only, because you are depleting it. When I say depleting it, it is not 100% depleted. You will have some the noise, background charge carriers produced, but the charge carrier from X-ray photon dominates over this. So you have electron hole pair produced, that is collected. That is the basic principle. So you have a depletion region in semiconductors. When X-ray photon interacts, you have charge carrier produced, that is collected to give out signal. And in scintillators, you have the incident radiation, then you have scintillation radiation produced from scintillator, because you have once again the same photoelectric effect or those kind of uh, phenomena happens. The secondary electron produces scintillation there, of scintillation in there. So this scintillation light is collected using what is called photomultiplier tube or photodiode. So they work once again, the photo multiplier tube. You have a photo cathode, which when the scintillation light hits that, you have electrons produced. That electrons is are multiplied. And in photodiode, it is, as I mentioned before, the light is sensed. The light produces electron hole pair here and sense. So hence, this is how you have high energy, especially for gamma rays, high energy X-rays. You have scintillator as the efficient techniques. So that is about the different types of detectors. You have looked at optics. You have looked
Sir,
at,
uh,
yeah, right.
sir, I apologize for the interruption, but we have
Yeah,
a
no
couple
problem.
of questions in the chat.
Okay, no
Sir,
problem. You can read
yeah,
out because if I go
yes, sir,
back to the,
yes.
yeah, yeah,
I'll read out. Abhishek is
yeah, yeah.
asking, sir, why do we not have LAXPC in spectroscopy section?
Okay. LAXPC is not, see, LAXPC is a gas proportional counter, and these are not very good spectroscopy system. But having said that, it can do a spectroscopy in much larger energy band. The what I meant is energy resolution. See, when we say spectroscopy system, we look at its energy resolution. So that is not as good compared to a semiconductor detector. So that's why we typically don't call them as a spectroscopy system, because we can have much better the moment you call it a spectroscopy system, you will compare it with other spectroscopy system. But these are gas field detector, they don't provide a good spectral resolution. So that's why we don't call them as spectroscopy system. Having said that, a broader spectral range, spectral resolution is available. So we call in energy bands. So within this energy band, like that. So am I clear? Hello. Yeah, I
Yes,
hope I answered your question.
yes, sir,
So
yes.
basically, the gas field detectors are not very good spectroscopy system. That's why we don't call them as spectroscopy system. Yeah. So
Yes,
what
sir,
is the
he
other?
says. Yeah, we
Yeah.
have another question. Pranjal is asking, does each ionization detector form a pixel in the imaging process, or are they not used in imaging?
Yes, see, when I say ionization, if you look at the gas field detectors, they cannot be used in imaging because you cannot provide that kind of pixel resolution. Of course, there are techniques, but it is not, very good resolution as such. But if you take, let us say, CCD, at the end of the day, even CCD, every pixel acts as a small ionization detector, because the X-ray photon interacts within that pixel, produces ionization, and you have, since it is semiconductor, you have electron hole pair produced. So it is used in imaging. But gas ionization detector, they're not very good imaging detectors again, because you cannot get kind of resolution. If I go back here, so here, for example, this anode wire, simple anode wire, at the most it can be used as a one dimensional imaging detector, but with very poor resolution, because the kind of resolution what you can get in um, um, CCD in terms of pixel resolution in microns. Here it is not possible to get. So you have, broadly, when you call ionization detector, you have gas ionization detector as well as semiconductor detectors. In semiconductor detector, it's possible to get the imaging. That's how you get imaging detectors. But in gas ionization, it is not very good imaging resolution what you can get. It is within the pixel, the ionization happens that time. Yeah. I think if any supplementary question is there, they can ask once again later. So is
Yes,
there
sir,
any more
that was it
question?
for now. No, sir,
Yeah.
that was it
Okay.
for now.
Okay. So we go back to, so we looked at different systems like gas ionization, semiconductor, scintillator. These are the only three techniques which are majorly used. And it is the four techniques: timing, spectroscopy, imaging, polarimetry. And it's the three technologies: gas ionization, semiconductor, and scintillation. And now little bit on what actually happens, because I understand this is, the if you have to do analysis, that is data analysis, X-ray data analysis. Even I would say, lot of people should start working on the instruments, because the modern astronomy is driven by great instruments. There are a lot of great instruments to be built and to be flown. But even if you are doing data analysis type of work, one need to understand basically what happens in the instrument. So apart from detection, how the signal is generated, the raw data, what you look at, what does it mean? So if you have that knowledge, the fun is different, and also you will get a lot of insight. And let's briefly look at it. So you have in any of these detectors, these are all these are all x-rays. We are talking about x-rays. In x-rays, the every photon is counted. That means every signal what you get corresponds to one x-ray photon. Note it, every signal corresponds to one x-ray photon. So each detected photon or particle, rather one event, that event in the in x-rays, it is one photon, because x-ray flux is much low in number. So you have photon by photon coming and entering your detector. So each detected photon or particle will appear as a pulse of electric charge. So on the right side you see here T0 to T1. So you have within the detector T0 to T1 set large number of charge coming and collecting. This large number of charge is caused by one event, that is one X-ray photon. For a certain duration it comes. So now if you look at the total charge here, that is QS, that corresponds to the photon. Now this total charge produced depends on the energy. QS is proportional to energy. So if you know the total charge, you know what is the energy. Okay. So, sorry, I did not, I missed putting some example here in semiconductor. If 6 keV photon comes, you have in silicon 6 keV, that is 6,000 electron volt divided by 3.6 electron volt. That is the 3.6 is the required energy for one electron hole pair production. So you have 6,000 EV divided by 3.6. That is about 1,500 electron hole pair produced for 6 keV. So this QS will be 1,500 electron. So and this duration T0 T, that is the charge collection time. So that event will produce a cloud of charge. That cloud is collected totally. That is typical time you can see here. Very thin silicon detector in picoseconds to nanoseconds, and thick detectors you have in milliseconds. Proportional chamber, that is in nanosecond to millisecond. And all this range, because it depends on the size of the detector, depends on the voltage you are giving, and depends on the parameters, operating parameters. And then there are some different types of detector like microstrip or gem, gas electron multiplier type of detectors, which are in nanoseconds, and then scintillators once again picosecond to millisecond. So the total, the point here is, within this time you would have collected that particular event. Why this is important is this decides what is the ability of that detector in timing experiment. That is, one event, say let us say one event takes 1 millisecond here to be collected. That means that will be the limiting factor for your timing resolution. So for a given application, you have to choose the right detector and parameters, configurations, so that you are achieving that kind of uh, timing resolution. Okay. And then you have photons arriving randomly. So they are randomly. So these are, let us say you have first photon coming of particular energy, the second photon another energy, So you will have larger charge produced, and you may have different energies coming at randomly at different times. So arrival of radiation quanta is a quantum random process governed by Poisson statistics. And then depending on the application, so you want to look at timing, then you are looking at the time of arrival. So you are looking at the energy, then energy measurement you have to do. So you are looking at the minimum detectable signal, whether it has come or not. Just for imaging, you may want to do that, or you may want to do combination of that. You may want to do imaging and spectroscopy together. So depending on all this, so your configuration instrument configuration is based on the application, based on the technology you are using, and based on the the kind of performance what you need. So there are two modes of operation. One is current mode of operation. Current mode means you have randomly arriving photons, but they are coming so fast that before you reading out one event, you have another event coming, etc. So in that case, you cannot really look at the event wise information. There what you do is you measure the average current, so we call it as current mode of operation. So let's not get into a lot of details, but basically the current will depend on the rate and the total charge, rate at which the events are happening and the total charge produced. So that is the current you look at. So this is typically used in the when the rate is high, like a dosimeter, etc. And pulse mode operation is an important operation mode for X-rays, because almost all X-ray detector systems work in this mode operation. That means here every pulse is red, every event is red, as we just discussed. And this is the only way you can do spectroscopy, because spectroscopy means you have to differentiate every photon energy you have to detect. So you have to do it in pulse counting mode. And again, examples we already looked at: proportional counters, that is gas field detectors, semiconductor detectors, and high Z semiconductor detectors like CDT, CZT, and the scintillation detector. We already looked at it. And this also I'll just skip because it's the same thing. And yeah, so here every all the X-ray detectors are photon counting, in contrast to other those which are used in other wavebands. And when you look at the basic X-ray data, it usually has list of events and their attributes. Their attributes like the time of arrival, and the other aspects like the for that particular during that particular event, what are the parameters, temperatures, etc. Because they are all important to derive the final to analyze your final spectrum. And images, spectra, and light curves are created from these event list. So you are getting it in the event and you are creating all these, and each time tagged event, because every event is time tagged, may be representative of your position in the case of position sensitive detectors, or representative of energy. And then of course data analysis techniques are developed for the source analysis using these events. And then coming to other important, uh, I have up to 12:40 or so I will target, then we can have discussion. Is that okay? Yeah, I guess it's okay. Okay. Then coming to the how you take the science, you have to extract reliable science from these instruments. So there are very important things. What is called instrument calibration is very, very important. It is the most important thing when you build an instrument. And we have to have gain and spectral resolution appropriately calibrated, in the sense during the observation, what is the gain of the instrument, That gain is nothing but your output corresponds to what sort of input, or what energy. For example, in the case of spectroscopy, the output corresponds to that particular energy. So that has to be calibrated properly, because the detector may be operated at different temperatures. At those temperatures the gain will vary, and the spectral resolution also will vary at different temperatures. And all those things have to be calibrated both on ground and if possible on board also. And then we have to calibrate means accurately you determine at the different conditions what is the effective area, what is the efficiency. So effective area we already discussed, it is nothing but geometric area and efficiency together. Geometric area multiplied by efficiency gives effective area. These are derived on ground for the devices or for the system, or on board using standard cosmic sources, or source, onboard source, using onboard source, etc. We can do many of these calibration. So calibration is a very important aspect. And then there are some other, if you are looking at the spectroscopy system, there are other calibration things like what is called spectral redistribution function, SRF. So here, when you look at the left side is a typical spectrum. This is not from celestial object, this is from moon's surface, but nevertheless it's an X-ray spectrum. This is for class payload developed by our team, which is working on lunar orbit. So looking at the moon's surface, moon's X-ray fluorescence. And here if you see, for example, you take calcium line. So ideally, the calcium K alpha is a single energy. However, due to many factors, some of the things are physics. That is the what is called Poissonian noise, short noise, and then electronic noise. All these things will cause this single energy to spread. Then another thing is, because of the device structure, the detector what you are using as a structure, you have different structures. In earlier, for example, I'll just quickly go back here. Here if you see, there is a structure, there is a metal layer, there is a P plus layer. The sensitive layer is only this. But what happens to the X-ray event happening in all these layers? Some of the things are blocked here. Suppose something is interacting in the at the interface, that will also contribute to the signal. So you have a single energy will show like this here. Say for example, this is about 8.11 keV. So 8.11 keV will show the response like this. You have a peak, you have a sharp falling edge, and then you have what is called shoulder. This is due to the device structure, and also the way event happens, and it takes certain time to travel across the drift distance and go to the electrode and get collected. This has to be properly calibrated, otherwise you will not be able to fit your spectrum. So this is done usually by using what is called monochromatic source, a single energy source. You characterize your device for a single energy source, given energy, what your device looks like. So like this you have to do for different energies, different energies, then create a matrix, what is called spectral response function, or the matrix has to be generated for different energies, and that has to be used in your data analysis. And also theoretically also, these models are created by knowing exactly the device structure, as well as the physics, the interaction physics, the transport physics. After the interaction, the charge carriers are produced. Those charge carriers are drifting and drifting uh, in the detector. So by knowing all these physics, put all these physics, and you can create theoretical model. So SRF is a very important study one has to do. And also other important things are like background modeling. You have to, because you are not just looking at the signal from the source alone. There may be other sources other than the sources which are of interest, which is in the background you are observing. And then there is instrument background. Instrument background means you have particles coming from galactic cosmic rays. They hit the device instrument surroundings. It can produce secondary photons, and also the instrument itself will be sensitive to those particles. That will also create event like X-ray event that can mimic X-ray event. So you have to determine all these things. And also the galactic cosmic ray model you have to take into consideration. So all these background aspects has to be considered when you get a raw spectrum from uh, spectrum from the instrument, and you have to consider all these before you really derive science. So that is about the technique, instruments, and some of the important aspects like calibration and background, etc. And this, I don't want to dwell deep into these detectors, these examples, but I just want to take you through some of the instrument which are in the sky right now by made developed in India. You have scanning sky monitor. Probably yesterday, Dr. Ramadevi would have talked about it. These are proportional counters, gas field detectors. You can see the timing spectrum obtained here, and the how the flux varies with time. And similarly, lax PC, someone asked question also why it cannot be used as spectrum. They are also, the gas field detectors. The spectral resolution is not great. However, the effective area for the the lax PC provides one of the largest effective area in the class of detectors. So it will have large sensitivity. That means in a short time it can get a lot more flux than other instrument. So you will have more confidence in telling your analyzing your spectrum. And then you have CCD used in SXT, soft X-ray telescope on rather astrosat. And here this is a good spectroscopic detector, and also imaging, because here X-ray optics is used. And then you have CZTI. This is the imaging is through coded mask. Here one of the first image here, crab through coded mask. But these are hard X-ray telescopes. Energy range you can see. Cadmium zinc telluride detectors are used. And class, since it is a X-ray instrument, I am putting it here. It is for surface chemistry of moon, to study the surface chemistry of moon, to generate elemental maps. That is the elements uh, which form which are the building blocks of the rock on the moon surface. And here is a typical spectrum. You can see the kind of resolution what it can give. And this is the map, the magnesium map. There are a lot of papers have been published here. Here we have used swept charge device, SCD. It's a similar to CCD, but slightly different way it is read out. So the advantage here is a large area you can have, and we wanted a large area. We cannot use optics for these missions, so we used large area, that 64 centimeter square geometric area itself. Um, so that is used in class payload on Chandrayaan 2. And the same set of detectors have been used on expect payload on Chandrayaan, rather Exposat. You can see the first light. You would have seen, some of you would have seen in the in a public outreach in when we had the first light of Cassiopeia A. It gives this source, this spectrum, and here Tycho spectrum. So these are all the result of this particular instrument developed. This is developed in our team, and once again using swept charge device with the collimators. Here collimators are used for restricting the field of view 3 by 3 and 2 by 2. Then SDD, silicon drift detectors, are used in Aditya, and also Chandrayaan 2 orbiter by PRL team, and in Aditya by our team. So here the advantage of silicon drift detectors are they can give good resolution like silicon. Also, they can handle much higher count rate. So if you have a large area of silicon drift detectors, it will have very good timing resolution for a astronomy mission. You would have heard about Loft. It was a proposal only, but it is not going up again, definitely, and which was based on silicon drift detectors, where which had the high timing resolution, and once again developed by our team here, high energy spectrometer for Aditya. This is CDT and CZT detectors. You can see the kind of spectrum light curve obtained, and also the spectrum energy resolved spectrum. And Polix is on, Polix is a polarimeter instrument, the first polarimeter instrument developed by RRI team, Process Biswajit and team. And this is based on Thomson scattering. When X-ray photon comes, and the scattered photon, has a preferential direction along the polarization direction. So you have a scatterer here. You have gas filled detectors, proportional counters all around. So scattered photon goes in, if it is a preferential direction because of the initial polarization direction, it will follow a particular emission direction. So the detectors detect them. This is the actual hardware, and this has once again the collimators, which is 3 by 3 FOV collimators. The scatterer is beryllium scatterer here. And just one more thing is about one of our current activity, that is soft X-ray polarimeter, which we are developing in our team. This is gas electron multiplier based detector, a refined holes which has high electric field when you apply potential across the surface, and that will create multiplication. And here the X-ray photon interacting with the gas medium, the photoelectron emission direction. Okay, I missed once again the putting that relationship. The emission direction is preferential to the electric field vector, and if you get the image of the photoelectron and its track, then you can find the emission direction. So that by you can determine the what is the polarization angle. So these are the simulated X-ray polarimeter simulated track of photoelectron. So you can see, a track, is of the order of 1 mm maximum. So that track has to be imaged. This is our some of the images which we collected in the lab. This we have proposed for future missions, and there are a lot of other things like I not put more on the future what is happening here, like the similar polarimeter, the Compton scattering-based polarimeter is being developed by well, developed at PRL, based on scintillation detectors, and then large area detectors for timing experiment, that is GRB, and gravitational wave counterpart detection. The instruments are being developed at IIT Bombay. They are calling it as Daksha. So these are some of the developments which are going on, and these soft X-ray polarimeters are being developed in our lab. We are also developing large area CDT detectors. These are some of the developments what are going on. So I this is all I have planned actually. So thank you very much. I hope you are able to follow some of these things.
Yes, yes, sir. Yes. Thank you very much, sir. We immensely appreciate your time and the effort that you have put in for delivering this session. I mean, you inspired all of us for this field. We have two questions right now.
Yeah, sure, please.
Should I should I say it?
I can, yeah, I am seeing some of these things. I think there is one sec, the C channels that we have already discussed. So since we are integrating the total charge in a particular time width, how do we differentiate if a high signal is from a photon of high energy or multiple photons of low energy? Yeah, it's a good question actually. So in X-rays, when we talk about celestial object, they are typically of low flux, that is in the kilosecond, or I mean, yeah, so our detector speed, readout speed, is much higher than the incoming flux rate. Okay, so that is why we will always say that the single photon, it is a single photon counting of those cells. However, these kind of situations are always there. For example, SXT or Chandra or some of these detectors, they are CCD type of detectors, and CCDs, as you know, take their own time to read out. You have to clock them. Clock, say one photon event has come, the charge is generated, and you have to clock them before you really read them. And that clocking time takes certain amount of time. But there are some bright sources which are really, which from which the photons may arrive at much faster rate. So you cannot see those bright sources with these instruments like XMM and Chandra. So you have to have the configuration or the choice of detector such that it is resolvable the time wise, the photon by photon. And otherwise, what, as you mentioned here, the two photons form can join together to form to make one signal. So that we call typically as pile up. Pile up can happen. So this also one has to calibrate, what is the typical pile up rate of that this pile up characterization is required. That also has to be accounted when we do the source analysis. Isn't the effective area a proxy for different resolutions? Uh, Let me try to understand this question. Isn't the effective area a proxy for different resolutions? Not really. It's basically, the sensitivity in the sense. Uh, uh, I mean, how efficient your system is, not just detector. It's all put together. How efficient in detecting certain quantity of flux. I have shown you one example where, if you can go back to that. My screen is visible still. Okay.
Yes, sir, your screen is visible.
Okay, I will just go to one of the effective area slide. Yeah, here if you see, basically, within this energy, for example, 0 to 1 keV, within this energy, uh, Chandra, Chandra has poorer efficiency compared to XMM Newton. That is the meaning. Poor efficiency means it has, the Chandra needs a lot more flux to give the same, um, uh, same, or it has to observe for longer duration. So the efficiency within a given time is higher for XMM Newton in this energy range. So again, going back to the questions, can we able to integrate interferometry in X-ray telescope? Okay, X-ray interferometers are being discussed, not yet, but since basically you need two telescopes for these, but these are being discussed. But it is possible. This will be the futuristic mission. Probably, you guys will have to take up these kind of futuristic missions. Yes, you can do that, and you can get much finer resolution, angular resolution in this. Would you please make the recordings for the participants? What is that? So that's all, I think, in this chat box.
If anybody has any other questions, they
Any
can
other question? Yes,
we
they
can
can unmute.
end the
Yeah,
session.
yeah, right. So anyway, before I end, I really call upon you guys to take, the experimental astronomy or experiments are really interesting. They are full of physics. So I am sure some of you will take more interest there sometime, and be part of astronomy community in building cutting edge instruments, and you can lead the teams in building big instruments. Also, one more information is X-ray optics is something which we started recently, X-ray optics development. So that's a very challenging activity, because the scale and the skill required is quite a lot. So we are working with the industries and other academic institutes in developing these. But we have initiated this activity for future imaging instruments, X-ray imaging instruments.
Sir, we have a question. Sir,
Yeah,
in
sure.
imaging, is the effective area more important or the geometric area for the FOV?
Both are important. See, geometric area will not tell you what is your effective area. Ultimately, effective area is the one for all sort of instruments, whether it is imaging, polarimetry, timing, or spectroscopy. The effective area tells how sensitive your instrument is. So even in imaging also, you have to collect more. Basically, nothing but image. The effective area tells you how effectively how effectively you are collecting the photons, and that the geometric area is just a geometric area will not tell you anything. I showed you an instrument with the what is that collimators, mechanical collimators. Their detector geometric area is about 64 centimeters square in the case of class. But however, because of the collimator, it has a lot of blocking area also. It has only smaller, only 80% open area fraction. So that will reduce it that much. So geometric area on its own has no meaning actually in any of the system. And you take optics, optics also. So the if the geometric area will be if you consider open area of fraction of the optics, the optics reflectivity also has some effect. So you may have one set of optics of a particular coating will have certain reflectivity, another set of optics of another uh, coating means the surface coating, that may have different reflectivity. The overall effective area may be different. So it is the effective area which is used for comparison and understanding the capability of the instrument. Yeah, something.
So I guess that's it for the question. And someone is asking for a contact, like if can we get your contact? Okay.
Yeah, sure. So I go to my slide, so you can note down this. You can see. Can you see?
Yes, I'll copy it. I'll write it in the chat. Yes, sir. Thank you, sir. This was like a really helpful session and thank you for your precious time. Thank you everyone for joining.
Okay. Thank you very much.
Thank you.
That's all. I'll log out.
Yes, sir. Sure.
Okay.